Okay, this is the Math 3 Unit 1 Whiteboard review for the Unit 1 test. Number 1, graph the following function, or 1 and 2, graph the following functions. So the first function we know is quadratic, because I have parentheses raised to the second power, which means I have an x squared. So anything to the second power tells me it's quadratic. I know it's negative, so it's going to open down. And it's going to be the upside down U shape. This negative is opening down, but the U shape is for a quadratic function. Another thing I need to realize is there's no slope with a quadratic function. So I cannot use this negative 1/3 as a rise over run. I have to find other points. So the first thing I'm going to do is make a t-chart that has our x values and our g of x values, where we're going to solve using our order of operations. And I usually want to find my vertex first for the quadratic function. So I know, based off of the behavior of a quadratic function, the value I would plug in for x to make this equal to 0 inside the parentheses would be -2. Now, I can use that information to go left 2, because it's the value you're plugging in for x, but it also means the opposite of this +2. The reason I want to find the opposite is so that this equals 0. You can plug that value in and solve, or you can use it as a translation. This means left 2, down 1. So from the parent point, which for quadratics, the parent point is 0, 0, I would go left 2 and down 1. Well, let's see if we get the same point when we plug it in. So I plug in -2, that's correct. When we solve, -2 plus 2 is 0, 0 squared is 0, 0 times -1/3 is still 0, and then at the very end we do 0 minus 1 is -1. That is the point I got for the vertex by using the translation from the parent point as well. So we can confirm that our vertex is -2, -1. You can just use your translation, left 2, down 1, to plot that point, but for the next point, you need to plug in an x value that will work well, to solve. So I could plug in -1, because it's right next to my vertex, my x value of -1, but if I do that, I'm going to get -1 plus 2, which is +1. 1 squared is 1, and then I'm going to multiply by a fraction. I'm going to get a fractional answer. So in order to not get a fractional answer, I want the part that's inside parentheses to be able to be divided by 3 eventually, so that I don't get a fraction. So what's a number I can plug in for x so that x plus 2 is divisible by 3? If I plug in 1, 1 plus 2 is 3, which is divisible by 3. So that's -1/3. Plug in the 1, add 2, and square it, and eventually subtract 1. So order of operations says parentheses first. We're going to do 3 squared, which is 9. I'm running out of room here, so I want to keep going. 9 needs to be, let's see, let's do it down here. -1/3 times 9 minus 1. Be very careful at this point. 3 squared is 9. We want to put it in parentheses because we have to do multiplication before we do subtraction. So -1/3 times 9 is the same as 9 divided by -3. which gives me negative 3 minus 1, which is negative 4. So I plug in 1 and I get negative 4 over 1 down 4. So when I plugged in 1, how far apart is negative 2 from 1? So negative 2 is 1, 2, 3 away from positive 1. So I want to go 3 in the opposite direction. 1, 2, 3, which will give me negative 5. And I should get a symmetrical point because I know that my axis of symmetry goes right through my vertex. And if this point is 3 to the right, I have another point that's 3 to the left, which would be negative 5, negative 4. On your test, you will have to graph 3 lattice points, which means I need whole numbers. You can plug in negative 1 and get a fractional answer and plot that on your graph, but it will not count as a lattice point. A lattice point are use integers. Lattice points use integers. Okay, so that's it for number 1. I have graphed what I predicted with 3 lattice points. Number 2, absolute value is a V-shaped graph. If it's positive, it's going to open up. This is an absolute value function. I'm going to make my table. I know if I plug in the opposite of negative 3, positive 3, that's going to help me find my vertex. So plugging in positive 3, 3 minus 3 is 0, 0 plus 1 is 1, over 3 up 1 is my vertex. Again, you can get this by translating from the parent point of 0, 0 for the absolute value function. That would be to the right 3 up 1, right 3 up 1. There's my point. After that, for absolute value, you can use a slope. My slope here is 1, which means rise over run, up 1 over 1. But for absolute value function, you don't want to go down 1, back 1, because it's not linear. It's linear absolute value, which means I have to take all the positives of my slope. So if my slope is positive, up 1 over 1, up 1 over 1. If you're not sure, you can always plug in x values. So 1, 2, 3, 4. If I plug in the number 4, I'm doing 4 minus 3 plus 1. Like 4 minus 3 is 1. The absolute value of 1 is 1. 1 plus 1 is 2. That checks out. Yes, I got over 4 up 2. You can do the same with positive 2. Once you have 3 lattice points, you can graph your function. So it's a V that opens up, just like I predicted. For number 3, there's A, B, C, and D. A and B are on the front side, C and D are on the back side. We're going to use number 2 to make some reflections and translations. So the first one is a reflection. And if I say a negative f of x, that's my function has been reflected. The whole function has been reflected, which means all of my y values are opposite. So we're going to say opposite y values. Well, I need to know my original y values in order to find the opposite ones. We're going to plot each of these points, but instead of plotting the point, we're just going to make a little indication of where it used to be. Because on this function, I'm not actually plotting points there. I want the opposite y values of those points. So these points are 2, 2, 3, 1, and 4, 2. If I want to take the inverse of f of x, then I need to take the inverse of all of my y values. So instead of positive 2, I'm going to have negative 2. The 2, 3, and 4 for my x values are going to stay the same, but all of my y values become the opposite number, and I'm going to plot those points. So 2, negative 2, 3, negative 1, and 4, negative 2. We can also see that the distance from the x-axis is the same for each of these points. So between this x and the x-axis, I have a vertical distance of 2 units. I can go down 2 to plot that point. This vertical is 1 unit, this vertical is 2, so I go down 1 and down 2 to plot those points. This is a reflection over the x-axis. If we reflect over x, that means our y values become opposite. Okay, part B, this means the inverse of x, or we're going to find our opposite x values. We're still starting from those original 3 points that we found in number 2, but this time we want to find the opposite x values. Okay, so we can just find if my original point was 2, 2, 3, 1, 4, 2. My y values are going to stay the same, but now my x values are going to become opposite. So I have negative 2, 2, negative 3, 1, and negative 4, 2. Oops, that was too close. So you can see that we reflected this time over the y-axis, or the f of x. On the back side, we're going to plot those same 3 x's, and then we're going to translate our function. So my original 3 are there. This right here is talking about if you were to plug in x plus 1 into your function, what would happen? But we also recognize this as a translation. In our translations, if we are talking about plus 1 happening to the x value, we know that the opposite happens, and this moves to the left one. Same thing here, but this time it's outside the parentheses, so it's happening to our f of x, which moves our function down 2. Down 2. So we could just take each of those and translate and go to the left one for part C. And for part D, you're just going to move each of your original points down 2. For part 4, I have a piecewise function. So I have part 1 and part 2 of this piecewise function. Each of my problems here below has a different x value that you're trying to evaluate what the function equals. So if I use negative 5 as my x value, I know that negative 5 is less than negative 2. It is not greater than or equal to negative 2, so I can't use the second piece. I can only use the first piece, which means my answer is just 5. For f of 0, 0 is not less than negative 2. 0 is greater than any negative number, so I have to use the second piece of my function, and I'm going to plug in that x value of 0 into my x above. Negative 2 times 0 is 0. 0 minus 3 is negative 3. F of negative 2. My x value is negative 2. I cannot use my first piece because x is not equal here. So this would be like saying negative 2 is less than negative 2. Not a true statement. Negative 2 is equal to negative 2, or greater than or equal to negative 2. So we have to use our second function again, plugging in that negative 2. And then we'll subtract 3 from the end of that. Thank you. So we're going to do 4 minus 3, which is 1. So my answer for part C is 1. Part D, I'm going to plug in 5. 5 is greater than negative 2, so I'm going to use the second function again.
River Sneed, Gianna.
Negative 2 times 5 is 10.
Petro Picardo, please report to the attendance office.
Sorry, negative 10.
Gianna Picardo, River Sneed, please report to the attendance office.
Negative 10 minus 3 is negative 13. For number 5, I have a graph of an exponential function. I already graphed it here, but let's talk about how I found this, because you want to make sure that you're graphing this correctly. You can always plug in points in order to find what we're graphing. If I plug in a negative value for x, I would get, let's try that. Let's try a negative 1. I would get 3 to the negative first power plus 1. Well, we know that for negative exponents, that means we move the base across the fraction line, which would make this 1 over 3 plus 1. It is okay to have an answer of 1 1/3, which would actually equal 4/3. It's okay to have negative 1 4/3 as a point, but it is not a lattice point, so it would not count as one of the points you plot if you're asked to plot 3 lattice points. So here, this is a fraction for my y value, so it's not a lattice point. It's between lattice points. That's why I chose to plug in only 0 or positive integers. So I plugged in 0, 3 to the 0 power is 1, and 1 plus 1 is 2. That's how I got 2. I plugged in 1, and 3 to the first power is 3, plus 1 is 4. Now let's plug in one more together, because if I plug in 2, that'll also be on the graph. So I'm going to plug in 2 for my x value. 3 squared is 9. And 9 plus 1 is 10. So plugging in 2, I get 10 over 2 up 2, 4, 6, 8, 10. So let's draw this function again, but this time going through all 3 lattice points. And then something else you need to not forget to graph is your asymptote. My asymptote is whatever number we're not going to cross. So this gets, these are going to be fractions, and they'll get closer and closer and closer to 1, but never actually hit 1.
Jenna McKinney, Nathan Fuller, please report to the attendance office. Jenna McKinney, Nathan Fuller, please report to attendance.
So I can tell that from my function that this is going to shift my parent function up by 1. My parent function has an asymptote at y equals 0, so when we shift it up 1, this becomes y equals 1. You will get docked if you don't graph your asymptote on your test, because I need to know what number you're not crossing. Alright, number 6. State the type of function for each interval. So from negative infinity, these are all domain values. So these give you x values here. So if I'm going from negative infinity to positive 6, that's right here. This value here is exponential. I'm sorry, that function is a piece of an exponential function. From negative 6 to negative 3, that's this V shape here that has a vertex at the top, so that is linear absolute value. Okay, and then from negative 3 to positive 1,
River, sneeze.
that's the U
Please
shape.
report to attendance. River, sneeze. Please report to attendance.
We know the U shape, whether it opens up or down, is quadratic. And then from positive 1 to infinity, it's a constant line, so that makes it a linear function. Move to the back side. Number 7. So part A should have been the domain. So this function on the left, from left to right, this is going up forever because it goes off the graph. You can put arrows on there, but it goes to the left forever and then it goes to the right forever. So my domain is negative infinity to positive infinity. The left side goes up forever, the right side goes down forever. So all of my y values are also used, negative infinity to positive infinity. But now we need to write an equation for certain parts or pieces of this function. So this is a piecewise function. We're going from negative 6 to negative 3. So this point right here, go ahead and write it down if you don't already have it. This point is negative 3, negative 2. This one up here is positive 6, I'm sorry, negative 6, 1. So left 6 up 1. The vertex is at negative 5, positive 4. So we'll talk about the other points after we write this equation, but I know for an absolute value function, my form for vertex form is m times x minus h plus k, where the x minus h is in absolute value. The h and the k stand for the vertex, so if I plug in a negative 5 here, I already have a minus, then a negative 5, which is going to change that to x plus 5. Okay, we know that if it's inside absolute value, that means to go to the left 5, and we did. We went left 5, up 4. The k value shows the up 4 at the end. Then after that, we just have to find the slope. So in absolute value, you can count rise over run. You can use the slope equation. So the formula for slope is y2 minus y1 over x2 minus x1. If you're ever not sure through rise over run here, you could always plug in your points. My y2 is 4. My y1 is 1. So here's my 4 and my 1. My x2 is negative 5 and my x1 is negative 6. So when we subtract a negative, that's the same as adding the positive. So I get 3 over 6. Sorry, I did my... Sorry, that's not 6. So I get 3 over 1, negative 5 plus 6. Sorry, I was not looking at the negative 5. Negative 5 plus 6 is 1, so I get positive 1. So my slope is 3, but we know that this absolute value is opening down. So I need to remember that that should be a negative slope. So this is a negative 3. Okay, for part D, I want to go from negative 1 to infinity, which is a quadratic function. This vertex is at 1, 2. This point over here is at negative 1, negative 2. So I'm going to determine my quadratic function. I know it's opening down, so my a value has to be negative. I'm going to write out the vertex form of a quadratic function. Very similar to what we did above, but this time I don't have absolute value. I have parentheses squared because that tells me it's quadratic. I'm going to plug in my h and my k. My h is 1, and my k is 2. And I can't use slope by doing rise over run. I can't find the a value by using this formula up here because a and m are different things. So I'm going to need to plug in another point. Let's go ahead and plug in negative 1, negative 2. So that's my x and y value, or x and f of x. So I'm going to plug in negative 2 for f of x and negative 1 for x. Negative 1 minus 1 gives me negative 2. Negative 2 squared is 4. So this gives me negative 2 equals 4a plus 2. I want to subtract the 2 to the other side. And now I can divide by 4, and I get a is equal to negative 1. So my answer will be f of x. I'm going to plug in the a value of negative 1. And I still need my h and my k plugged in, so it's going to be x minus 1 in parentheses squared plus 2, and that's my answer. Another way you can find your a value is if it's a whole number. If you know this point right here, which we did not, I didn't give it to you, 0, 1. If your x value directly to the left has a whole number and hits at a lattice point, then that should be your a value. So directly to the left, I'm going down 1. That's where the negative 1 comes from. That only works directly to the left and directly to the right for those 2 points. It does not work like a slope. You don't go down 1 over 1 to get that negative 1. So that's why we always want to make sure we're plugging in a point in order to solve to be absolutely positive that that's the a value. You can write this with or without the 1, but the negative has to be in front of the parentheses. Number 8. Graph and describe the transformations. So I have 1/2 of absolute value of x minus 3 plus 2. I'm going to go ahead and graph this using the vertex and the slope. I'm going to graph both of these using the vertex and the slope. You can use an XY table and plug in your points. But for absolute value, since we can use a slope, I'm going to use the rise over run. So my vertex is whatever number I'm going to plug in for x to get 0, which is positive 3. That means to the right 3, then up 2. Whatever number I plug in here to get 0 would be negative 2, down 1, meaning negative 1. And then the slope should be the same. They're both 1/2, so rise over run. Let's plot f of x and then label it after we plot it. So my vertex is right to 3, up 2. Remember, this means go to the right 3, but we found that when we found the vertex. And then my slope, up 1 over 2, is going to give me symmetrical points in either direction, making this V shape that opens up. You need at least 3 lattice points, 1, 2, 3. I did 5, and that's okay. Now we're going to graph g of x. So let's make sure we know which is which by labeling f of x. Plotting g of x, we're going to go negative 2, down 1. And again, my slope is rise over run, up 1 over 2. Up 1, back 2. In order to determine the transformation from f of x, I wrote g of x. Sorry, transformation from f of x to g of x, we're going to count from our vertex of f of x to our vertex of g of x. We're going down 1, 2, 3, left 1, 2, 3, 4, 5. Down 3, left 5, or left 5, down 3. That's our answer. Number 9, determine the equation of the composite function f of g of x, then graph the function with at least 3 lattice points. So right here, f of g of x is you're taking g of x and you're plugging it in for x into the f of x equation. Okay, so the g is inside the f. So we get negative, and we're going to use parentheses wherever we plug in a value. Negative x squared means we plug in the x plus 2 where we see the x. F of g of x is negative x plus 2 squared. My vertex here is whatever you plug in for x to make this equal to 0 inside the parentheses. So left, or negative 2. Up, there's nothing being added to the end, so 0. Left 2, up 0 from the origin. It's quadratic, so I am going to make a table. I have a negative 2 value here, so I'm also going to plug in the point on either side, negative 1 and negative 3. If I plug in negative 1, I get negative parentheses negative 1 plus 2 squared. Negative 1 plus 2 is 1. 1 squared is 1. But the negative is out in front. We do that after we do the exponents. So we multiply by the negative, and I get negative 1. So this is the point, negative 1, negative 1. You can do the same for 3. Plug it in, use your order of operations to solve, or you can use your axis of symmetry. And I know that my -1, -1 is 1 away from my axis of symmetry, so I go 1 in the opposite direction to make a symmetrical graph. Okay, here's a way to tell if your function has an a value of 1 or -1. Every x and y value should be the x value squared to get the y value in the distance away. So if I go from the vertex over 1 down 1, 1 squared is 1. If I go over 2, 2 squared is 4. If I go over 3 from the vertex, 3 squared is 9. So the next point will be here. 3 squared is 9. And the negative just means it's opening down. If it was a positive 1, it would be over 1 up 1, over 2 up 4, over 3 up 9, over 4 up 16, etc. All right. So we're going to, we already graphed using 3 lattice points, so we're going to move on to the back side. This is the last question, is a piecewise function that has 3 pieces. So we're going to start with piece 1. Whenever I see a restriction, I want to know what my function equals at that restriction. Sometimes I will have an open point, sometimes I'll have a closed point, but I still want to evaluate what the value is there so that I can figure out where the function is going. I'm going to highlight x equals 0 so that I know piece number 1 is to the left side or less than 0, and it'll keep going forever that way. I'm also going to highlight my x value of 2, and my x value of 3 to show that piece 2 should be between 0 and 2, and piece 3 should be between 0 and 3. I won't have anything right on the right side of positive 3 because I have no x values that can be greater than 3. We'll talk about the domain and range at the end, but starting with our first piece, this is a quadratic function. Where my vertex is -2, 0. And I don't know my I know my a value is 1, but I can't use it as a slope. So I make sure to plug in numbers. So if I were to plug in -2 plus 2 is 0, 0 squared is 0. That's where the vertex comes from. So -2, 0. This is my vertex. But I also want to make sure to plug in my restriction. So my restriction is at 0. So I want to plug in 0 plus 2 squared. I'm going to change this so that we can show which piece of my function I'm plugging it into. I'm plugging it into x plus 2 squared. Okay, 0 plus 2 is 2. 2 squared is 4. So 0, 4. I need to tell whether at that restriction I have an open or closed point. If it's not equal to, it must be open because I don't actually have a value that I can plot a point on that function. 1, 2, 3, 4. So open point at 0, 4. This is quadratic. If this is the vertex, I know I have a symmetrical point in the opposite direction, but that point is going to be closed because if that value is -4, I know -4 is in fact less than 0. 0 is not less than 0. That's why I had to do an open point here. I could also find two more values if you plug in -1. You get +1 squared, which is 1. So you can continue to plot these points, but you only need 3. But you do have to have the restriction point and the vertex. And then I need to see something on the other side of the vertex so I can see the U shape of your graph. So that's quadratic, that's why it's a U shape. Okay, for number 2, we have a linear function, which means I can use my y-intercept, which is +2, so 0, 2, and my slope, which is -3, or -3/1. Now I need to know whether or not that y-intercept is an open or closed point. So when I have -3x + 2, I could also plug in my values. When x is at 0, it's equal to, so I want a closed point. When x is at +2, I also have less than or equal to, so that's also a closed point. So the line underneath the less than sign is going to tell you whether you have an open or closed. Line underneath means closed. No line means open. So if I plug in 0, that's just 0 + 2 is 2. If I plug in 2, that's -6 + 2, which is -4. So I'm going to go ahead and plot those closed points at 0, 2. And 2, -4. And we can see my y-intercept we already knew was going to be 0, 2. From the +2 at the end, y = mx + b. But I went ahead and plugged it in anyway. So if you want to find the slope in between here, or the points in between here using slope, you would go down 1, 2, 3 over 1. Down 3 over 1 also gives us our last point. And that's linear, so it's a straight line. And then piece 3 is exponential. So I'm going to use, because there's only 2 numbers here, I'm going to use each of them. I'm going to plug them in, 2 and 3 for my x values. So that gives me 2 squared and 2 cubed. 2 to the second power is 4. 2 to the third power is 8. And we're going to see which points are open and closed. So this one does not have an equal sign. So whenever x is equal to 2, I'm going to have an open point, which is at 2, 4. And when x is equal to 3, I'm going to have a closed point because I do have an equal to sign there. So this one's going to be closed. So 2, 4 is open over 2 up 4. 3, 8 is closed. And you want to make sure you draw it curved because it is an exponential function. My domain, my x values, this side will go to the left forever. This will keep growing and growing and growing to the left. So my domain goes from -infinity. Let's see if there's any holes as I go across. There is a hole here, but that x value of 0 is used at this point, so then I keep going to the right, to the right, to the right. There's a hole here, but that x value of +2 is used at a point, so I keep going. And then my x values stop. I have no x values that are greater than at this point right here, which is positive 3. And we can look at this up here too. All of my negative x values are less than 0. Then all of my values between 0 and 2 and between 2 and 3 are all used. But no values greater than 3 are used. So the maximum of my domain is 3. That's going to be a closed point because that 3 has an less than or equal to sign, and x can equal 3. We can have a closed point and it's equal to. The range is going to go from bottom to top, so the very low side of my range is negative 4. It's a closed point, so I'm going to use a bracket. Then as I go up, I want to see if I have any holes, so all of these y values are being used. This y value of positive 4 is a hole at 2 different points, but the good thing is it's used right over here, so we will use the y value, so we just keep going. And then this function stops here, but this left function continues forever, so that's going to go to infinity. That's it for the Unit 1 whiteboard review. You have some homework posted on Google Classroom, so make sure you check what assignments are due.